All right, so last time in the last video, we started talking about different reproductive strategies, either having few offspring that have a large parental investment in them, either in nutrients or parental care, or having huge numbers of offspring with little nutrient provision and zero parental care. And these two life strategies have names: K-selected species and R-selected species. And you'll notice this one, this capital K here, is the same K for carrying capacity. And the lowercase r here is also deliberate. That lowercase r is for reproduction. So K-selected species tend to live near the carrying capacity of their environment. K-selected species are more likely to be found in stable environments that don't change a lot from year to year. They tend to have few offspring and a large parental investment. And R-selected species tend to have many offspring with no parental investment. And R-selected species, the reason we use R for reproductive capacity is because R-selected species have the capacity for huge population growth, explosive population growth in the right conditions. So if we have a species that matures extremely rapidly, which, flies mostly fall into that category. Fruit flies, which are often studied in the lab, fall into this category. So if there's an abundant food source, like in the fall for fruit flies, when there's a lot of rotting fruit around, fruit flies will have a population explosion because they have an extremely short time to maturity, about 2 weeks from hatching out of their egg to being sexually mature. For a fruit fly is about 2 weeks. And each individual female can lay several hundred eggs every few weeks. So that's an enormous potential for population growth right there. Now, normally in a stable environment, our selected species get stuck at the carrying capacity just like everybody else. But if there's a sudden increase in resources, our selected species are ready to go, and they can have a huge population explosion if there's a sudden increase in resources, which could be, for example, if they discover a new environment. For example, invasive species. Invasive species that are R-selected species tend to be the biggest problem because they have a huge potential for reproduction. For example, starlings, which are, I don't know, there's debate about whether they're actually invasive, but they're certainly non-native. They are from Europe. They were deliberately introduced to the United States, and they have certainly had explosive population. And starlings, unlike a lot of birds in North America only reproduce once a year. They have 3 or 4 babies, and then that's it. Starlings can have nests of 7 babies, and they can have 3 nests a year. So they have a much higher reproductive capacity than some of our native birds in the U.S. And so they've taken over the niche that previously was occupied by the passenger pigeon, which is extinct. Now we have starlings. Plants can also be R-selected or K-selected. So, for example, dandelions are R-selected. They produce huge numbers of tiny seeds. So, poor nutrient provision of their offspring. The seeds are quite small. They also disperse very easily. And so they can have a huge population boom if the resources are right. Like if suddenly they are, let's say somebody has been using weed killer for years and a new owner moves in and stops using weed killer, well, now there's this lovely area that they can exploit. So they could have a population explosion in that one area. Other types of plants have high provision of their offspring with nutrients, like, nuts are large seeds. Coconuts are the largest seeds. So there's a high amount of parental investment in the offspring. So they cannot produce as many seeds as a dandelion because they're putting so many nutrients into each seed. So that's the same idea. So Brazil nut trees are not going to have a massive population explosion because they don't produce as many offspring. But each individual offspring is more likely to survive. With something like a dandelion or a fruit fly, in an ordinary year, most of their offspring are not going to survive. But for something that has fewer offspring, like a robin that only has 4 babies a year, each individual baby has a higher chance of survival because of the level of parental care. So density-dependent factors also regulate population growth. So a density-dependent factor is something that changes as the population increases. So density-dependent factors tend to slow population growth as the population either gets close to carrying capacity or exceeds carrying capacity. Other factors are independent of the population size. So something like a drought that might decrease population size, that has it doesn't matter how dense the population was, that's not going to cause a drought. But limiting the amount of food that a particular species eats, as the population increases, food becomes more scarce. So that's a density-dependent factor. So density-independent factors can affect reproduction and population density, but they are independent of the actual population size. So things like climate, droughts, fluctuation in food availability that's not based on this particular species eating that food resource, those would be density independent. Density dependent populations, as the population increases, those density dependent constraints will tend to decrease the birth rate or increase the death rate, or both. So here's some of the density-dependent factors that we'll talk about in more detail. Competition, interspecies competition, territoriality, this is also between species mostly, increased disease prevalence, predation, intrinsic factors, we'll talk about what that is, and also accumulation of toxic wastes. So if a population is very dense, whether we're talking about plants or animals, all individuals of the same species, so that's, one population, individuals of the same species use the same resources. They have the same ecological niche. So they are competing against one another for resources. And this will tend to lower the reproductive rate because the food nutrients are going to become scarce, or possibly even nesting sites are going to become scarce. If a population is tightly packed, as populations get denser and denser, and this would be true of any animals or plants, disease can spread more easily. Diseases that spread from individual to individual, generally diseases affect only a single species at a time, and if many members of that species are close together, disease can spread more rapidly. We all have learned a lot more about this year. Predation. So if a prey population becomes very large, predators may start to feed preferentially on that species. And this is just because of learning. So if a species, if a predator is successful catching a particular kind of prey, they have learned something. They've learned that they can catch and eat that particular prey, and if they see another one, they might choose to go for the exact same prey, even if other prey are available. So having a large population, if you're prey, could mean that you're going to now be targeted by the local predators because they've had success with that particular species catching them. Species have evolved elaborate strategies to not have predators become dependent on them. And here in the US, we have several species of cicadas called periodical cicadas that don't emerge every year. We do have annual cicadas that emerge every year. So we do hear some cicadas singing every year. Periodical cicadas, though, are spread around the Midwest and the eastern and southeastern United States, and there are different groups of them. There are 13-year cicadas and 17-year cicadas. Here in northern Illinois, we have 3 species of 17-year cicadas that, even though they're 3 different species, they all emerge together. And the brood that's here, so these different, even though they're different species, and one emergence might be 1, 2, or 3 species, they call them broods, and they all have Roman numerals, so we can talk about what year they're due. And the brood that's here in northern Illinois has 3 different species of 17-year cicadas, and they call it brood 13. That's our brood that's here in northern Illinois. They last emerged in 2007. There aren't a lot of them in Kane County, but they're found in huge numbers in DuPage County. And their strategy is to emerge by the millions all in the same year so that predators can't get them. They overwhelm the predators that are present. Predators eat them all day long, and there's so many of them that many of them reproduce. And they're very noisy, and if you did not live here in northern Illinois in 2007, if you're going to still be here in 2024, that's when the next big emergence is set to take place. And especially towns like Elmhurst are absolutely overwhelmed with these 17-year cicadas. Last summer in 2020, because of course, 2020 was the year of weirdness. Some 17-year cicadas emerged early in places in the Chicago area. And the question is, were there enough of them to escape the predators and lay enough eggs that we're going to see them again 4 years early with the next emergence? Most likely when they don't emerge in the right year, when a brood, individuals from a particular brood don't emerge in the right year, they just get eaten. They don't reproduce. So that helps maintain this periodicity. Because cicadas are very tasty, apparently, as my dogs will attest, that they love to eat them when they find them. Because they're not toxic, they're not bitter like a lot of insects. I've never eaten one, but my dogs eat them all the time. So look out for that. So this is 2021, so 3 years from now is the next big emergence of these. And it's in the summer when they emerge. So territoriality can also limit population density because it forces individuals out especially animals that have very large territories that they defend, like predators like bears and lions tend to have large territories, wolves as well. A pack of wolves will defend its territory from other packs of wolves, and they have very large territories. That keeps the population density low because they will often actually kill individuals from other groups, and this also forces young adults to emigrate, and it pushes them out. They will often chase away newly sexually mature young individuals because it's too crowded. There's not enough prey. So that keeps population density low. Some individuals, like certain rodents, when their population density gets too high, they will actually produce, there's hormonal changes in the females, and they will actually produce fewer offspring. They will ovulate less and produce fewer offspring. Other organisms, if they, this happens with a lot of animals, even if the offspring are born, if there's not enough food to eat, they will abandon their offspring because the mother wants to survive another year. And she can't do that if there isn't enough food for the babies. And I'm saying that like she's thinking and planning about that, but it's instinctive behavior. Production of toxic waste. So this would mostly apply to aquatic species and also yeast. So yeast are fungus. Their natural environment is rotting fruit. And they're eukaryotes, which don't divide very rapidly. It takes 60 to 90 minutes for a yeast cell to divide. So they're competing for resources in the rotting fruit with bacteria, which divide 3 times as fast. So through natural selection, yeast evolved the ability to produce a toxin as a waste product that poisons bacteria faster than it poisons themselves. So when yeast are fermenting sugar, they produced ethanol as a byproduct, which kills bacteria. And eventually, though, it will kill the yeast too if it gets high enough. Once the ethanol concentration is above 13%, the yeast start to die. The absolute maximum is about 15 to 16%, which is why you never see naturally fermented alcoholic beverages higher than a concentration of 15% alcohol, which is the high end for wine, for example, because higher than that and the yeast are dead. But bacteria, their competition, are killed at much lower concentration. So this could also happen with fish. Eventually, nitrogenous waste from the fish, if they're extremely crowded, will build up to the point where it actually becomes toxic to the fish. So population dynamics is the study of all these factors that affect population size, the biotic and the abiotic factors that cause variation in population size. Both of these factors can have an effect. Some of them are dependent on the species itself, others are independent of that. So abiotic factors would be things like weather, a really super cold winter or a year of drought. Those would be abiotic factors that are going to affect population size. Biotic factors would be an increase in predator populations could affect prey population size. And one of those is an experiment that's been done for decades now on an island in Canada called Isle Royale, where islands are popular for studying these kinds of things because you have limited immigration and emigration. If you're talking about something other than birds, there's not going to be a lot of immigration and emigration. Although, you know, on an island, moose can swim, and so can wolves. Wolves are less likely to swim than moose, but both can swim. But still, they would, if there's food on the island, they will stay on the island. So the population of moose and wolves on this island has been studied for decades. And what they found was that the moose population will increase as if there's available food. Moose are herbivores. And then the predator population will then increase. And then as the predator population increases, moose population decreases. Mostly because the wolves are mostly going to reduce moose reproduction by killing young babies. And then eventually there's not as much food to eat because the moose population has decreased. So then the wolf population is going to crash. Then the moose population will recover because the predator population is low. And so there's this kind of up and down cycling of predators and prey. And this has been studied with other species as well, rabbits and lynx, for example, and we see something very similar. So this cycling of populations is very well understood. They've even done similar experiments with paramecium with the same thing. Some paramecium eat other paramecium, and so they can have predators and prey of single-celled organisms as well, and they see the same kind of fluctuations. This is a little movie about that Isle Royale experiment. So I'm not going to show it to you because it's a few minutes long, but it's in the PowerPoint. You can watch it on your own. So another kind of population is if we have several nearby populations that have some immigration and emigration between them, but they're somewhat isolated. And all of those little populations together, we would call them a metapopulation because they're all one species. Each population is somewhat isolated from the other populations, but there is still some movement between those populations. So metapopulations are often really important because if there's an extirpation of one population, another population in that metapopulation through immigration might repopulate an area that has the appropriate resources for a particular species. So that's also something that ecologists want to take into consideration when we're managing endangered species. Are there multiple populations in different areas? Can we possibly use a healthier population to repopulate an area that, because of an extremely cold winter or something, declined? Can we help with using that? If there's only a single population of an endangered species, that makes that species much more vulnerable to extinction. So here's an example from a butterfly species that it's on a, again, island. Scientists like to study populations on an island because you don't get as much immigration or emigration out of the population. And every little dot represents an area where you could find this species of butterfly. And the black dots are where they found them in one particular year when they were studying them, and the white dots are areas where this species could exist. There are the right resources, and maybe they have found them in the past, but there aren't any there on the particular year they were studying. And this can be a way of determining if this species is declining or not. If it's disappearing from areas where it used to exist, that can give a lot of good information, and then scientists can ask why. What is happening in these areas where they're vanishing from particular areas where we used to find this species and now they're not there anymore? Human population is maybe one of the more controversial ones to talk about because some people don't like to talk about human population. Our population is no longer growing exponentially. It had been growing exponentially for several centuries, and it's not anymore. And it's really things were not very hopeful in the 1970s looking at population growth, but now looking at how the human population is changing, people are much more hopeful that we are going to reach some stable number without having to go through a big population crash, because no population can grow indefinitely. There are not indefinite resources. There are no planets we can go to expand our population. We just have here. So the human population grew very, very slowly for a long time. So our species has been around for about 300,000 years. Probably at that time, 300,000 years ago, our species, well, for the first almost 200,000 years, our species existed. We only existed in Africa, and population was relatively small, measured in the tens of thousands of individuals. Then, about 100,000 years ago, our species started to leave Africa and migrate out to Australia, to Asia, to Europe, and then much later, about 20,000 years ago, to North and South America, and all of the Pacific Islands even later than that. Within the last 10,000 years, all of the islands in the Pacific. So, this is a longer time span here, going back to at the end of the last ice age, 10,000 years ago. And the population grew very, very slowly. See this little dip here? I don't know if you can see that. If you're looking on your phone, you might not be able to see it. There's a little dip right here. That's the Black Death in 1350 that I mentioned before, where there was about 50% of the population of Europe and Asia died multiple times. And so the worldwide human population, because not everybody was affected, the Black Death did not affect North and South America. The Black Death did not affect African populations. So that's why it's a small dip, even though 50% of the people in Europe and Asia were killed. But, you know, that little dip in the human population was enough to cause the little ice age. So the population started increasing exponentially. So something changed here. And this is a blow up of this little portion here since about 1700. So, and if you remember, the mid 1700s, that was the Industrial Revolution. So what happened then that could have affected the human population? Burning fossil fuels does not help people live longer. So what happened? And we think that it was roads. That once there was extensive roads year-round and trade, it decreased famines. Periodic famines were no longer occurring because the human population was no longer isolated. And we also had increased urbanization. So you can't have a huge increase in population unless you start to grow urban areas and cities where huge amounts of people are living in a small area and none of them are farming or hunting. They're all getting their food from the countryside. So that's really what drove this increase in population, is those two things. A switch from everybody growing or hunting their own food to an urban population that's producing other things and is now dependent on other people for food, and also roads, so that you don't have famines. Populations aren't as isolated anymore. So, and you can kind of see at the very top here in this graph, there's kind of a little bit of a tailing off. So the very first person to notice that the human population was now growing exponentially was actually in the 1700s. Thomas Malthus wrote an essay called On the Principle of Population, which you can find. There's PDFs easily available online. And he wrote this essay about how human population was growing exponentially, and of course, no population can grow exponentially indefinitely, and he was saying there's going to be a big famine or disease or something, and the human population was going to crash. And luckily, he was wrong. His essay is also interesting because if you notice the year here, this is not long after American independence from Britain, and Thomas Malthus was a Brit. And so he's very negative about Americans, and he talks about Americans don't have the wonderful system that Britain had, where you have an educated overlord and a bunch of peasants being told what crops to grow and what livestock to keep. Instead, you have all the peasants deciding for themselves what crops they're going to grow, and they don't know how to farm, and they're all uneducated, illiterate peasants having lots and lots of babies. And yeah, he has lots of negative stuff to say about America. He said we were doomed because we didn't have this system that they have, the feudal system that they had in Britain at the time. So, but it's kind of entertaining to read that stuff now. Our population today, thankfully Malthus was completely wrong, and we're up to about 7.8 billion. However, we're not growing exponentially anymore, and it started to become apparent in the 1980s that the population growth had actually slowed down starting in the 1960s. So here's the latest population forecast from the United Nations. This is from 2019. They do one about every 10 years. They do an updated world population forecast. And so here's the measured population up to 2019 here. And then these lines all represent different projections based on predicted population growth rates, with the red line in the center here being what they think is the most likely outcome if trends in decreasing fertility rate continue. If those trends continue as they have been since the 1960s, that we're going to stabilize and reach zero growth in this century. in the 21st century, and we're going to stabilize at about 11 billion people. And many people are extremely alarmed by this. I even saw an article yesterday about lamenting the fact that there wasn't going to be a pandemic baby boom, that it's quite clear that people are choosing not to have a baby during the pandemic. And I don't find this alarming at all. I think the human population reaching a stable number where the population is no longer increasing, and maybe even if the population decreased slowly, that would probably be a good thing. But some people find this very, very alarming information. I disagree. I think a constantly increasing population, and depending on having a huge population of young workers to support the elderly population, is a terrible system for an economy because of this. Because this is happening. Even governments that have tried to encourage people to have more kids have failed. People are making the decisions based on their own lives and not listening to that. But I'm happy about this. I'm very happy that it looks like we are approaching a stable number. So another way to look at this is by the annual percent increase in the human population. And if this just only goes back to 1950, when population was still going up really fast, the annual increase in the population of around 2% has been steadily declining. And you notice down here at the bottom would be 0% increase. So when we hit the bottom of this line here, that means our population is stable and no longer increasing, which I think would be a good thing. Me and a lot of other people. This big dip here, this was due to a famine in China that killed millions of people and prompted their one-child policy because they crunched the numbers and realized that this was going to happen again if they didn't decrease their population growth. Another way to look at it is the rate of doubling of the human population. So it took a really long time in the past, thousands of years, for the human population to double. But finally, going from the year 1000, there was about 250 million people in the world, to 1650, where there was 500 million. So it took 650 years for the population to double. Then for it to double again, only took 154 years, doubling to 1 billion by 1804, and then 127 years to double again to 2 billion by 1927. Isn't that weird to think that in 1927, there was only 2 billion people? Then 47 years to double again. You can see these years are getting shorter and shorter. So this was extremely alarming. So by the 1970s, there was a lot of alarm about the human population increasing because they thought this number was going to keep going down, right? So, but it looks like it's going to be 50 years before we get to 8 billion. We're forecasted to reach 8 billion in 2024. So that's good. You can see the rate of doubling is slowing. So to keep a population stable, there can be two ways to do that. One is to have a high birth rate and a high death rate. The other is to have a low birth rate and a low death rate. And what has happened, though, the reason we had this explosion was because initially this was the human population, right, during when we were hunter-gatherers and, before the Industrial Revolution. High birth rate, high death rate. Average number of births per woman was 6 before the Industrial Revolution. But half of those kids wouldn't live to age 5 on average. And the population was very stable because of a high death rate. Then the birth rate stayed high, but the death rate declined. And that's where you get a population explosion. So pre-industrial, high birth rate, high death rate. Then the birth rate stayed high for several hundred years, while the death rate declined. And the birth rate in the United States, or the fertility rate, I should say, up until World War II in the US was still, the average number of children per woman was still around 5 to 6. Probably quite a few of you have grandparents or great-grandparents who were from families that had 12, 13, 14 children. That wasn't unusual in the early 1900s. To have a family of more than 8 kids was not unusual. But then finally, the birth rate has been declining. And some of the reasons for the decline in the birth rate is education. So the longer girls go to school, the fewer total children they're going to have. So having universal education through age 18. If you start having babies when you're 12, you're going to have more babies in your life. Postponing that first baby, and the year keeps getting later. I believe right now in the US, the average age of first baby for women is about 25, and it keeps going up. Also, increased work opportunities for women. So what's happening right now, we can see this happening in countries where the birth rate is falling. Women are going to school, and then they're getting a job because they want to have some money before they have kids. And it's also part of this change from rural to urban, because in a rural society where everybody is farming, your kids are your free workers. You need to have kids to work on the farm. But once everybody is, or most of the population is urban, kids aren't your free workers anymore. Kids cost money. You got to send them to school, you got to buy them stuff, and they're not earning any money anymore because it's not a farm. So the birth rate, those things drive the decrease in the birth rate. So women want to go to school, get a job, and earn some money before they have their first baby. And that's what's happening. We can see it happening. So another way we can look at populations, human populations, is the age structure of the population. How many kids, how many reproductive age adults, how many old people are there? And these change depending on where the society is. I'm going to go back a slide. On here, that will change. So let's look at some of these pyramids. Now they call them age pyramids because for most of human history, we had a pyramid that looked like this. And now this is essentially, these are graphs. These are bar graphs. So on the bottom here, we have numbers of people, and this expressed as a percent of the total population. So these are bars going this way. So this is the x-axis down here. The y-axis goes up the middle, and we have females and males on either side. And then ages, and they're broken down by 5-year age groups here. So here are the kids here. Pre-reproductive kids are the bottom 3 bars. And then we have reproductive adults up through age 40. So the next 5 bars, those are your reproductive age adults. And then you have your post-reproductive older adults at the top here. Now, for almost all of human history, the entire human population looked like this, with lots of kids. So kids here are at least 50% of the total population, if not more, and fewer older people because before antibiotics and without good medical care, you have a pretty equal chance of death at every age because of infections and accidents and whatnot. Well, finally, after post-industrial, birth rate declines, so we have fewer kids, and life expectancy has also increased in the older ages, although not as much. Most of our increase in life expectancy is due to decreased infant mortality. So this is what it looks like currently for the United States, where you have pretty equal numbers at every age until we get over 60, but fewer kids, more adults. So the kids here, if we're going to count only the pre-reproductive kids, the bottom 3 here, so kids 15 and under here, they are not half of the population. They are much less than half of the population, maybe a quarter or less of the population. And then here is go even further, Italy has an extremely low birth rate. Italy is actually, the birth rate is below replacement levels. So the population of Italy is going to start declining over the next few decades because of this, which again is alarming to some people. I do not find it alarming at all. I think that we are probably over the carrying capacity already. So our population declining and stabilizing, is going to be just fine. It's going to be okay. You can see that actually they have much fewer kids. The average family size in Italy right now is 1 or 2 kids. Having only one child is very popular right now in Italy. And then they have a large number of middle-aged people, and this boom here in the middle, this baby boom, is slowly moving its way up in the population. And we can see the boom here, baby boomers, is this little bump here, the people who were born after World War II. So this is what happens during industrialization. So we're probably heading for this kind of a societal structure. Italy's a little bit ahead of us. We'll probably get here in 20 years or so. So infant mortality has a big effect on life expectancy, because life expectancy is the average age of death. So if you have a very high infant mortality, if you have half of individuals not surviving to age 5, that's going to bring down the average age of death a lot. So when you hear numbers like, oh, during hunter-gatherers, days, the life expectancy was 35. Well, that doesn't mean that nobody was around who was older than 35. What that means is that because infant mortality was high, like 50% don't get to age 5, the average is going to be low. But we have definitely found remains of individuals from hunter-gatherer groups, ancient hunter-gatherer groups, who were definitely in their 60s or 70s based on their bones. So individuals did live to old age. They would have just been less common than they are today. So when you hear, the life expectancy is increasing, it's mostly due to a decrease in infant mortality. If you compare, what are your chances of living to 100 if you made it to 65 200 years ago and now? It's about the same. So people who made it all the way to age 65, your chances of continuing to live for a few more decades are the same now as 200 years ago. So medical technology has not really increased life expectancy in old age, but what it's done is make it more likely that you get to 65 in the first place because of antibiotics and reduction in death from accidents and vaccines preventing childhood illness that tended to cause death in the past. And life expectancy can go down. They're expecting life expectancy in the United States to go down over the next 10 years, mostly because of diseases related to type 2 diabetes and heart disease. So that would be the first time that had happened. And also, we don't have the lowest infant mortality in the world. I think the U.S. is 25th or 26th in the world in infant mortality, and that's mostly because we don't have universal health care. And a lot of infant mortality is due to the fact that women don't have medical care during their pregnancies, and sometimes even right after they deliver. So what is the carrying capacity for humans if we consider the whole planet? This is an area of hot debate, with some people putting that number as low as 1 billion, saying we're way over the carrying capacity already, and others saying that it could be as high as 30 billion or even more. But, 8 to 10 billion is the average estimate. But really, we don't have a whole lot to base this on. It's a lot of calculations, and it depends on what resources you think people are going to use. So it's the question, are we already over carrying capacity and we're in the process of using up our resources? Or are we approaching our carrying capacity? Either way, if the real number is somewhere in between 8 and 10 billion, we're going to slightly overshoot that number. But we don't really know, and we'll know a lot more 50 years from now, seeing what the human population does in the next 50 years. But some of the things that go into the calculation is how much land does it take to grow enough food for the estimated number of people? What kind of food are those people are going to be eating? How much wild food are those people going to be eating? For example, fish. Fish stocks have declined enormously, and they have a less of an ability to feed people now than they did 50 years ago. So that has to go into the calculation as well. Climate change is going to have a big effect on that. So when we're thinking of the ecological footprint of a population, we want to know how much land and how much water it's going to take to sustain those individuals. And is that water going to be easily available? So here in Illinois, we don't have any limit on water. We have the Great Lakes close by. We have groundwater that is not going down. We have plentiful rainfall, and we do not have a water shortage here at all. But there are other areas where that is not the case, and the population is going to be limited because of the amount of water that's available, because of course humans need fresh water. Water, if it's a very arid area without a lot of water, that's also going to limit crop growth as well, because crops would need to be irrigated. So we have to take all those things into consideration. So this is somebody's estimate of the ecological footprint of different countries based on the amount of land and resources that are used by individuals in that country. So red is high, 6 hectares more than 6 hectares per person for the red countries. So US, Canada, Australia, one Scandinavian country, which I'm not sure which country that is. I think Sweden. And then, the rest of Europe, not far behind, and with 3 to 6 hectares per person. So if we're going to ask what is the carrying capacity of the planet, if everybody is like us, it's a very different calculation. Another way to look at ecological footprint is just looking at energy use. This will become less of an issue if we use more solar and wind power than relying completely on fossil fuels. So, and there's a picture here of this is a composite satellite image of the night sky, and because obviously we couldn't get all this picture at one time, showing the highest energy uses places where you can see lights on at night. That would be an area of high population density and high energy usage. So we'll know a lot more 10, 20, 30 years from now, but climate change is certainly going to have a big impact on what the carrying capacity of the planet is for humans and other species.